get you to sleep. So Comet Toolbox, I talked about that a couple of hours ago. This is the same slice from the other presentation. And this time we go a little bit deeper into what the usage of Comet and also some a little bit about the installation of Comet, how to get it work, and how it's supposed to work in general. So we have this class-like structure on the right side, which basically consists of 3 parts. There's on the right side is the user input, so the information that you need to model or invert some kind of MRS or MRT data. And then you have the class components from the Comet software that are single objects in Python that you need to fill with information and that you that gives you access to the source code itself. So you run it script-based without a graphical user interface, as I said before. I can show you how that's done, and then basically you communicate with these classes to get the working flow done. Let's say, and then for the when it comes to the installation of Comet, I got a API documentation online. As you can see, here's a link that we can, I don't know, post somewhere. And also, it's a Git repository where you can where you have access to the documentation. Inside the documentation, there is a installation guide for the different settings. So it's working for Windows, as you will see in a moment, I hope. And then most of the time, I work on Linux, however, because most of the larger machines that I use for the more complex stuff are Linux-based. It's somewhat easier. And also the complex magnetic field calculation is only working on Linux, as I said before. It's I don't want to show that today because it's not necessary. It's the same syntax, same kind of handling with the source code. Just takes a lot longer, a lot more time than we do have already. So small guide. Just I don't know if these presentations will go online. I guess anyway. So we have this command line interaction using Conda. Conda is an Anaconda package. Anaconda is a Python distribution. So what you need to run Python code is a Python distribution. And one way to go would be an Anaconda installation. It's a software that is free, at least for most purposes. And then you can install Anaconda as a software. So I maybe go outside again, and then we have this beautiful Anaconda Navigator as a software installed. There's a basic platform to run Python, or one of the platforms that is enable you to run with Python, and that's dealing with environments. So you have some closed containers where dependency for Python packages are handled for you, and in these containers you can install certain software, demand a certain software, and then any kind of dependency from the software is installed automatically for you. So we have this MS Windows environment that I created with the Comet software, and then we can use an IDE, so some kind of program that is able to run Python. You can also use bare console commands, but I wouldn't recommend that. So we have this script-based approach that we can use, and then you can, for example, download some of the examples from the website or from the repository, from the GitLab repository, and then you just basically run those and then see what happens. So this the first example, the most simple example for a synthetic modeling and inversion in 1D, but it shows use single commands that you will use throughout the entire thing, whether you model in 1D or 2D or any kind of thing. I mean, just shouldn't take that long. So tested a lot of things, obviously, but okay. It's not even starting right now. Right. Let's just do it another way. Okay. So if you're working on Windows or Linux, you need to activate the Comet environment, which is what you can see here. That is Comet is printing the active environment that you're working in right now. This is just a normal console. Then you have some kind of software that you can use to start Python, or you can start Python directly. In this case, I want to use the Spider software, which we just killed. And then see, I think there was some leftover commands from the testing earlier. So let's just get it running again, and then everything should work. Okay. So what we do here is we have normal Python commands that are just used to define some variables. For example, in this part, where we just get some lists, insert some float values, give them some names. In this case, we want a synthetic model that consists of thickness for 1D model, resistivity values, resistivity values, water content, and relaxation times, just simple lists. And then next thing, we use the first Comet class, which is a config configuration file. That is just for the 1D magnetic field calculation. So it's a primary configuration. There's also a secondary configuration file, which you will use for 2D. I don't show that today, but there's example files where this is used as well. Just as a container to contain information about the modeling. You can save them. You can load them from the hard drive again, and it's just a way of transporting information from one class to another. And then start to bake the basic layout as if you were in the field. So you're in the field, you have an idea of what's going on. You lay down your loop. In this case, we create a loop and a rectangle from -20 to 20 meters, so 40 meter then a certain discretization. We give them the config file, and then we have this class, and so the source code is already there. So then we, if we go here, we have this loop class initialized. It's a closed rectangle. It consists of a bunch of dipoles, which is usually how loops are discretized. You can use a plotting function, for example, to just see how it looks like. It's not very spectacular, but the way Comet discretizes sources is by a bunch of dipoles that are put on the middle of some edge discretization, and then they represent some part of an edge from a transmitter or receiver loop. And then for every dipole, a magnetic field is calculated. And the superposition of these magnetic fields are the magnetic fields of your receiver, transmitter, whatever. That is somewhat brute force. It takes longer than it sometimes is necessary, but it's also
just a question. For instance, we can define multi-node loops to calculate the kernel.
So I can jump into the MS live session. If you have the right bunch of corner points, and then you insert these corner points into a loop class, then you can so it is possible to create a multi-node loop.
Okay,
if you desire to do so. The problem with that, some drawback is the automatic mesh creation that cannot handle the yes. So I have to change that. But apart from that, it should be working. So yeah, that's the first thing I did today. Okay. Next thing. So we have a loop. Okay, we have some kind of setup. Now we gather this further into the main class of the Comet source code. It's the survey class. One survey is the survey you are in. You are in the field. You have a survey. You have a bunch of loops. You have a bunch of measurements. All of that is together in one survey. And this survey class is created as a bare class. So just from importing the right modules, you get the SNMR package or the PyHead is the magnetic field calculation for 1D. So from the SNMR package, you have the subclass survey, which just is initialized, and then you add your loops. You can add as many loops as you like, and then you define magnetic Earth. In this case, just whatever inclination, declination field you have, just a bunch of numbers. And then you create soundings. Soundings you can create also as many as you like. You define the transmitter and the receiver part, which is just an index to the loops that you previously added. So there's only one loop. In this case, we use this loop for transmitter and receiver part. So we have a coincident measurement. And then we have this site data container, which consists of one loop and one sounding. Very, very simple in this case. And then we start the modeling part. The modeling part is handling the physics of the NMR. There's two main classes. It's the MRS class for one sounding. And then there's the MRT class for a couple of soundings, which can be any kind of way, shape, or form. Just one of the MRS class is inverting only one sounding, and the MRT class is inverting multiple soundings, or modeling also. In this case, we have the MRS class. We provide the site. So the survey class that we had earlier, we define the index of the FID we want to invert. This is Python, so it starts counting by 0. So the first FID to invert is index 0. And then we want to have a block inversion, and we want to handle the data as complex data, not as rotated amplitudes, for example. So this is what we did. And then we simulated the data. And then, as the source code is already finished, we have this MS class. Whenever you want to know something, you can get to the console, print something in. So you get a bunch of information about what is going on. The MS class in this case is a, as I said before, block complex inversion. Got a bunch of pulse moments, which you can add or change, of course. Then you have a gating. The data is always stored in raw format, which means just a time series. The gating is done on the fly. And then you have the same as for an error vector, which we just defined in the simulation here. So we added the synthetic model and error level that we want to have, and roughly a number of gates. You can see there's 43 gates here, because gating is done in a way that fits the number of gates that you want to have. And then if the first gate doesn't contain data, they are merged together. So sometimes you are ending up with less gates than you want to have. We have a forward operator for complex modeling. We have a kernel that is ready for calculation, but also we have the inversion because it's already done. So then we invert just with the global smoothness constraint, and then we plot the results. In this case, we have these measured data for the real part, for the imaginary part, and then the misfit after the inversion, and some kind of model. Of course, it's fitting quite nice, because we use the same kernel function for synthetic modeling and for the inversion, which is kind of dumb, but it's just proving the point. Okay, this is an inversion engine that is running, and then that I can also invert some field data. You may just believe me that. Okay, so going a little bit further is example 2. Is using the 2D capabilities of Comet. So we did the same thing. We have imported the two libraries from Comet and also PyGimli in this case. We set some logging values. This is just how verbose the console is when talking to us. Nothing too fancy. We set a bunch of parameters, which is just strings and stuff like that, so you can change it if you like. Then we start the survey class, and then in this case we we load a previously filled up site with a synthetic data set. In this case, this data set looks like this. This is one of the survey classes. The file ending npz is a NumPy specific way of saving files. It's just a binary container that contains arrays, booleans, and then basic Python kind of stuff. So you can import it in Python, and you can also export it in any file or shape that you like. The way I organized it is you have the basic stuff in the first data container, and then you get one data container for each FID, for induction decay, and then one data container for each loop. And they might also have a second one for each loop for the configuration. So in this case, I have some let me see. I have some survey class here that I can show also. This is one entire survey. It's all linked together. You have the FIDs, it's 8 of them, and then you have 8 loops with their configuration files. And that's it. So most of the files are very, very small. The biggest files are usually the data container from the FID because they contain the data as well. And then sometimes the magnetic fields and also meshes are saved independently, but most likely not in the same folder, depending on what you are doing. So example part is finished, means we just run the 2D inversion in the background. After we import the data, we import our inversion mesh, which I previously generated, but also we can just have a short look. So we have the inversion mesh. It's a PyGimli mesh. So any kind of mesh that is internally used is in the PyGimli format. You can create, you can import most meshes from any kind of generation software that there are, like Gmesh or Tetkin. Tetkin is what we use. And then, or you need to define your mesh brute force by yourself, just the number of points and then how to connect them and stuff like that. It is the same principle for all mesh building stuff. So in this case, yeah. We can use the PyGimli library to visualize the mesh. It's a 2D mesh, so it should be pretty straightforward. In this case, this is our inversion mesh. I have some refinement area that I have, and then I have the sources as well that I discretize a little bit smaller, and then just get some for some boundary purposes. You get a little bit larger than it needs to be. Just figure. Let me just. Show you the loop layout because you got the question earlier, or you used the multi-channel thing. So what we did here right now is now it's a live session. We got the site; it's an empty site. There's no loops, no soundings, just a bare class. And now we want to import the previously saved one. Example 2. So I just imported the folder that I showed you earlier. So this folder is now in here, which means we have site 2 consisting of 8 loops and 8 soundings, because inside the loops, so we get to the plotting library, and we can take a look at the layout model. Yeah, it's a lot of loops and a lot of dipoles, so good. Maybe that was a bad idea. So anyway, moving on. If we have the inversion mesh included, then we set up the MRT class. We feed in all the information we have. In this case, the site, same as before. We have dimension 2 because we want to have a 2D inversion. And then the data type should be, I don't know, rotated amplitudes. We set the counter functions. I had to calculate them earlier. Oh, there it is. Okay. So this is the loop layout that we have, and that's the inversion mesh again. Sorry for the. Okay. So this is an ATRAS setup where there is a loop 0 is the transmitter in this case. It goes from -72 to 75 to 75 meters, which is underneath the other one because they're plotted on top. It's not ideal, but it's the large transmitter type, and then the small loops are just 20 by 20 meters, 40 by 40 meters, half overlapping inside this transmitter loop, which is the basic setup we have here, from -100 to 100, and then the inversion mesh goes from basically 200 to -200. So the MRD class is fed in. We have the data container inside, which is like this. In this case, it doesn't contain any more loops because I only want the data in here, and then get the kernel function from somewhere else because I can't calculate them on this laptop at least. So I had to move them from my other computer here. Then we create a forward operator, which is containing all the, doesn't need any input because it's always the same actually. We have the set rate and a lambda. So we have we have two constraints as well. We have the vertical direction can have another constraint in the horizontal, sorry. And then generate a starting model, and then we run the inversion and save the results. So if we save the results, we can use a plotting script. The results you can show in the folder is not that much. Just basically it's this container. As you can see, I inverted the complex version as well. And I just used the plotting functions. I usually, after the inversion, I just save it and call it a day. Because there's no point in having the plotting inside the inversion script if you need to run the inversion because you, I don't know, want to change a label or something. It's not making any sense. The basic plotting is done the same way. Also script-based in this case, you import the libraries. You set some file names that you want to import. It's the same that we use for the saving of everything. We include the site and we import the data. And then we use the MRT class because it provides us the load results thing, as it manages the different files and insights. And then we have the plotting library, which basically is in the by-head library, plot sub-library, and then you have different plotting types to show you the show loop layout. You can also plot meshes, and in this case, ITRA data, which then generates these example files. In this case, it's a special plotting function for the ITRA data because it's always the A channel, always the same type of plot. So I had made a shortcut for this one because for the coincident measurement, you have other amplitudes than for the other 7 because of the loop change in loop size. It's just one way of plotting it. You can also plot by yourself. Every sub command that is used to generate the plots is also inside the library. So you can just go to the function, see what's going on, change labels or whatever you like to have. In this case, this is data, misfit, and response plot. So again, the misfits here, just as a, inversion is done. And then you can also plot the model. Maybe it's a little bit more interesting. Same thing, we import all the libraries at the start. And we get the results imported. We have the model consisting of 2 parameters, in this case, so water content and realization time. And then we get to the plotting functions. In this case, we use PyGambly function to plot it because they handle the mesh visualization. usually comes with a lot of parameters that you can insert, but there's also a lot of example files, not only for Comet, but also for PyChem itself. So when it comes to plotting any kind of things, you can always find an example of what you want to do, and then it's easier to change the way the script works by changing a label or adding a subplot or whatever. Then you don't necessarily have to learn all the syntax of the source code just to make the first plot or the first inversion, stuff like that. So I would stick close to the examples at the beginning, and then if you want to change something from there, it's easier to do it this way, I guess. I think compared to the other softwares, there's no graphical user interface, and there won't be any graphical user interface anytime soon, because I wouldn't know of any people who can simply work this out. And then as long as you I guess get it running, so get an installation of Python and Comet running, and can start using the example files, you should be good to go. And if there's any kind of problem, I'm happy to help. Also on Git itself, you can create issues and stuff like that. I'm getting emails when there's something coming up, so I can try to react or fix stuff, or whatever. I think it's right now for the purpose of normal modeling and inversion should be at a state where it's able to handle most stuff. As I said before, I don't have an input routine for example, numerous data. So this is something that has to be fixed once. So a routine has to be implemented into Comet to import some special data container. And it's something that most probably I can do the fastest, because I know what needs to go where and whatever. So you don't need to do this by yourself. I think I will add an example where I just make it brute force, like I have a bunch of arrays for data, real data, imaginary data, time, and then just import those directly. So you can take this script and then you just change the arrays and you're done. Maybe that's the most general thing that people would need to start to get their data in and then start modeling and inversion stuff. Done. Something to do with the console. Anyway, as you can see, I didn't remove the areas. So rather small script. So then we have the model. In this case, just the final result. I don't know where the label is, so never mind. Yeah, there's plotting. So from import to setting up loops, I guess this is what at least has been used before. So